Hello, welcome everyone to PyCon 2019, day one, the first slot. Uh, how many of you are staying for the full thing? Tutorials, talks, and sprints. Anyone? Woohoo! Yeah. So it's my third PyCon, and trust me, it's one of the best conferences out there. You meet a lot of fun people. You learn a lot, and let's make this fun. So this is a tutorial on network analysis, and it's hosted by me, Mridul, and Eric. Woohoo. And I am a PhD student at UC Louvain in Belgium. I study network science and a bit of computational social sciences. And Eric is a research scientist at Novartis in Cambridge. So let's start. Again, if there are still any issues with the setup, please use Binder. And can we get a thumbs up? Everyone's ready? Yeah, yeah, yeah. Oh, before we start, a bit of housekeeping. There would be a break at 10:15, a snacks break, and lunch is at 12:20. And we have power outlets all around, so use them. And there would be a server link for the tutorial, which we'll post it later through the tutorial email. So before we start, let's just get our gears running. And so this is we have created a list of dictionaries, right? So can anyone tell me what would be this function if you want to find persons with the surname in this data structure? You don't have to write the code. You just have to tell the idea behind that.
This is notebook 0, by the way.
Yeah.
So if you want to look at it on your home screen.
Anyone?
4% and percents. If percent, square brackets, surname equals query surname, close and percent.
Yes. Yeah. That's a perfect answer. Yeah. So this is in this tutorial we're going to work a lot with lists and dictionaries. So it would by the end of the tutorial you would be pretty comfortable with working with that. And so just to present how the tutorial is, the logistics of it. So you see every notebook would have two versions. One is instructor and one is student. In the student version you have exercises. So if you want, I would suggest you actually work on the student notebook version. So you can go and actually solve the exercises, which is much more fun than just looking what's there. And if you're stuck, feel free to move to the instructor notebook and see the solution. That's totally okay. It's not an exam. And if I am too slow for you, that is okay too. You can and there is a lot of material in this repository. You can use this material for a 7 or 8 hour tutorial. So feel free to go ahead. So that's okay too. So let's start with the introduction. So this is a list comprehension. Can someone tell me what are the plausible data structures for S and my favorite things in this? S is a string. Okay. Yes. What else? What about my favorite things? Yes. So yeah. So you could see in here. This one is basically it's a string. It's an iterable of dictionaries. Yeah.
It could be anything with the dunder get define.
Dunder get. Yes. Yeah. Yeah. That's what. In standard data structures, that would be a dictionary. Yeah. So before we talk about networks, can someone tell me an example of a real world network they can think of? What is a network for you? Home Wi-Fi, yeah. And what are the nodes and edges in that network, according to you?
Phones, tablets, devices, everything that connects to it.
No, like phones and tablets are the nodes in this, and okay. Any other examples of what is a network? Social networks. So you have Facebook, Twitter, LinkedIn, right? Can someone tell me what's the like? Suppose there is a Facebook social graph and there is a Twitter social graph, right? Is there a can you think of a structural difference between a Facebook social graph and a Twitter social graph? Like what's the difference between Facebook? Like suppose I'm friends with you on Facebook, and suppose I follow you on Twitter. There is something different between the structure. Can anyone think of that?
Twitter doesn't have reciprocity.
Yes. So in this case, for Facebook, if I'm friends with someone, they're friends with me back. So it's there's no direction in our relationship. But on Twitter, if I follow some person X, that does not necessarily mean that the person X follows me back. So there's a notion of direction in this. So these are two basic concepts. It's like a Twitter is called a directed graph because you have direction, and Facebook is called an undirected graph because there's no direction. And one thing to keep in mind is the information, the heart of a network or a graph is its edges. Because just by looking at the nodes they don't give you any special information, but the way they are connected, that's the whole point of creating a network. So edges are the most important part of a network. So we have discussed the examples. So our hope is by the end of this tutorial, you would be comfortable with using the NetworkX API of how to manipulate data, how to create networks, how to model them, and how to analyze them. You should be able to visualize networks using some basic techniques, and you would be comfortable with writing some algorithms on using graphs, and computing some network statistics. And on a more conceptual thing, it's about how to think about network problems and how to map those interactions and create a network out of it. In network science research, there's a funny saying that everything, every problem in the world can be modeled as a network. I don't necessarily agree with that, but if you think hard enough, you can model everything as a network. So that's there. So reiterating on this, there is student notebooks and instructor notebooks. If you want to solve the exercises, which I recommend and which would be more fun, always open the student notebooks. And if you're stuck and if you're too tired right now, or if you're jet lagged, feel free to follow the instructor notebook too. That's okay too. I won't be offended. And feel free to skip ahead and just go full steam ahead till the end of the tutorial. And so this work has been inspired by a lot of previous different work, and much of this work is written by Eric in this repository, and now today he's TAing me. So the apprentice has become the master now apparently. So let's start.
Fun at that.
Whoopsie.
Just to interject a few points, midway through, if there are any issues, just raise your hand. If you have a question, raise your hand. I'll come by with a mic. And I'd really like to encourage people to ask questions for everybody. And the reason I have a mic is because we want to keep your questions recorded on video for the benefit of other people who might be watching the tutorial later, okay?
Also, this is a tutorial, this is not a talk. So please feel free to interject and ask questions. If you don't want to interject me, that's okay too. You can raise your hand and ask Eric. He can solve your problem. So, but make sure that this is not a one-way interaction. So and also that's not a one-way interaction. Feel free to talk with each other and create a network. You are the nodes and create new relationships. See what I did there? So let's start. So the basic building block of a network, in this case, are nodes and edges. Node represents some entity, some some person, a train station, a computer, and edges are the relationship between those things, between those people. So, and to understand the API of NetworkX, we'll use some data, and this is a very controversial data set, and we'll get to that later. So don't kill me for that, but this is a very controversial data set. Disclaimer. So, but before we do that, let's talk about data representation, how it's represented in NetworkX. So if you're familiar with Python, if you're familiar enough with Python, you'll see that this is a dictionary of a dictionary of a dictionary of a dictionary. It goes all the way down. So if you have done computer science or mathematics before and you know how graphs are represented, so you would understand what I'm saying. But it's a dictionary of a dictionary of a dictionary. So you need to be comfortable with playing around with dictionary. And in this notebook, we do that. So let's load this controversial data set. So this data set is a friendship data set. So some researchers went to a 7th grade class and asked a person, "Who's your best friend?" They said, "Ta-da!" But what if that person doesn't say that? Oh, I say person X is my best friend, but the person X is like, no, he's not. Person Y is my best friend. So this is a controversial data set. So let's see what we can look into this. Wait, what? Oopsie. Yep. So there are some custom loaders in here to load the data set into the graph. You don't need to worry about that right now. But if you're interested how they're working, there's a custom folder in the repository. You can look at the code there. So let's start with some basic statistics, like how many people are there in the graph. So to access nodes, you use something like g.nodes. And the only reason we're using NetworkX in this tutorial is because the API is very, very intuitive. Like, okay, you need to find the number of nodes in a graph, right? So we have G, which is a graph object. We do g.nodes. You get the number of nodes. You get something called a node view. You don't need to worry about that right now. You just get a list of nodes. And you don't get a list, you get a view of node. And you can typecast this to a list to get a list of this. And if you want to calculate the total number of nodes, you just use the inbuilt method length. So there are 29 nodes in this network. So far, so good. So I talked about casting this view as a list because it's a bug or feature of as you may like of the NetworkX API. As it moved towards 2.0, initially it used to be g.nodes returned a list, but now it returns a view. But you can't slice a view. Like you can't do this thing. It will give you an error. So if you want to select if you want to select like 5 nodes, then you have to first cast it as a list and then do the slicing. 0, 10, you have the first 10 nodes. So this is one thing to keep in mind if you are working with an older version of NetworkX. So things may break. So this is one thing to keep in mind. So the first exercise, can you write a single line of code that returns the number of nodes in the graph? Well, that was already done. Once you're done, give me a thumbs up. Yep.
Oh, thank you. When you cast nodes to a list and then slice it, are you guaranteed to always get the same nodes back? Like, is it ordered, or can it be different?
So according to Python, if you're using Python 3.8, 3.8 or 3.7, order is guaranteed because uh, because the dictionary underneath is ordered by default. But if you're using earlier Python 3, then no, you can't say it's guaranteed. But again, it depends on the order of insertion. So if we have the same order, like if we have the same notebook, we'll get the same results. If we have the same Python and NetworkX. Everyone done with this exercise? Finding the length, finding the number of nodes? Yep. So like one way would be just to calculate the length of G dot nodes, and another way is calculate the length of the graph, which is like these are some concepts from graph theory, which is like a length of a graph is known as the number of nodes. So if you do that too, you'll get 29 again. So now let's figure out the more fun part. Who is connected to who? Who thinks you are my best friend? Who thinks like someone else is my best friend? So again, just like nodes, very intuitive. You want to find edges. So you do g.edges. You'll get, again, something called an outage view. Again, don't worry about what outage view is right now, but you see you get a series of two tuples in which you have like a starting node and an ending node. And suppose you want to just get, whoopsie, just get some a sample of nodes. So we see that one is connected to 2, one is connected to 3, and so on. And here 1, 2, and 3, 4 are people in our 7th grade. So, yeah.
Does the directionality here or the order matter? Like, is 1, 2, like 1 said 2 is my best friend,
Yeah.
and the other way around or something like that, or does it not matter?
In this dataset, it matters because it's created as a directed graph, but we'll get to that later. In this, it matters. So exercise number 2, can you write a single line of code that returns the number of relationship, which means the number of edges in this network? We know how to get g.edges. Now you have to calculate the number of those relationships. Once you're done, thumbs up. So just like g.nodes, if you want to calculate the number of edges, we just pass in length and g.edges, which will give us the total number of edges in this network. And everyone got 376. Yep. Perfect. So now we are understanding what's the basic concept here, a network or graph. So the fight between network and graph is, if you're doing mathematics, you'll say graph because it comes from graph theory. And if you're doing data science, you'll use the word network because that's network science. So it's the same thing. It's not a different thing. And conceptually, it's a set of nodes which are joined by a set of edges. And for the representation, a node list is can be represented as a two tuple, where the first element is the node itself, and the second element contains metadata about the node. Can anyone think of metadata in this network? Like, we know every node is a student. What could be a metadata about every student? Yep, we have name. Yep, we can have the name. What else? Yeah, physical address. So we can have a lot of metadata about the node itself. And just like that, even with an edge, we can have metadata about that too. So an edge is a 3 tuple. You have a start or an end, like where the edge starts, where the edge ends, and data about that about that edge, metadata about that edge. Can anyone think of the metadata about the edge? What could be a example metadata in this data set? Yep. Yeah, like how strong their friendship is. So I mean, we do have something like that in this data set. We'll look at that. You had a question?
Question.
Is the number of edges associated to a node always going to be included in the metadata of a node? Likewise, is the direction of an edge counted as metadata for that edge?
I mean, that is data related to the node, but that's not exactly metadata because you can just count the number of neighbors, right? Like you can just count the number of neighbors and then you have that information. But yeah, I mean, yeah, that is kind of metadata about the node too.
I think that's a good point in that there's computable properties of a node, and then there's just intrinsic properties of a node. And the intrinsic ones are the ones we can't compute on the fly from the graph. So number of neighbors, yes, it's metadata, but it's the kind that you can just compute directly.
Yeah.
Whereas like in this case, what's the name of the student? That's intrinsic to the node, right? Yeah.
So like the graph we loaded in, it had a lot of metadata too. So to look at that, you need to pass in this argument data equals true. So if we don't do this, we'll get something like this, just a list of nodes. But if we do pass in data equal true, we'll get a metadata. We'll get the biological sex of the child of the student in the class. So you have gender for every node. And if you'll see, if you look at the data structure, it's a two tuple. You have the node, and then you have a dictionary which has information about that node. You can have multiple attributes, right? So that's why it's a dictionary. So you can have gender, you can have their name, where do they live, and many other things. So let's do an exercise again. Can you count the number of males and females in this network using the things that we know right now and your Pythonic knowledge? Just to give you a bigger overview, this is our data set. So we have 1 to 29. Some are male, some are female. The exercise is to count the number of males and females in our data. You have 3 minutes for this, and once you're done, give me a thumbs up. Woohoo. And again, if I'm slow for you, feel free to go ahead, and there are a lot of exercises to do. Just wanted to check. No one is stuck with the setup, right? Yeah, you are. Can you? People done with the exercise? Thumbs up. So does everyone get 17 females and 12 males? Yep. This is what you should get. And this is my answer of doing it. I use a counter object. This is not the only way of doing it. There are a lot of other ways of doing it. But till you are getting the final answer, that's more than perfect. So just like nodes, edges too can have this attribute dictionary. And in this data set, so like every student was asked a series of questions, and they were asked to pick up, like, who's your best friend in this case, or like something like that. Who's your best friend in this case, in that case. So you have this thing called count. The number of times 1 chose 2 is 1. The number of times 1 chose 6 is 3. And it's always between 1 and 3 for some reason. I'm not sure why, but that's the data. So so can you figure out the maximum time any student has rated any other student as their favorite? The answer should be 3, because so again, to reiterate the exercise, you basically need to find the maximum of this dictionary all through the data set. So if I check all like the full output of this thing, I have count dictionary in every edge, and I have to find the maximum of count in this list. Again, you have 3 minutes for that, and once you are done, please give me a thumbs up.
For those of you who might be a little bit confused, if it's the first time you've seen assertions in a function, that's a test. Tests are good. We can talk about them for all day long, but basically you won't see any output. If your function is correct, you won't see any output. Only if your function is wrong, then the assertion will fail and there'll be a big error.
Thumbs up if you're done with the exercise and you got 3. Perfect. Again, like in our answer, we use a lot of list comprehensions because, like, I mean, come on, it looks very nice and neat, and it's the Pythonic way of doing these things. But even if you're doing it without using these fancy list comprehensions, that's okay too. But we hope by the end of the tutorial you are convinced that this is the list comprehensions are a good thing. Yeah. Yeah.
So does this fall in your network topology? How many devices you have?
Sorry, can you,
Yeah.
for the benefit of others?
Okay, so let's say if you're trying to replicate this in a production environment, network environment,
Yeah.
like say data center or
Yeah.
internet edge. So using this module or dictionary, we can call out how many devices we have in the node which are active and polling back to us. I mean, I'm trying to correlate this to the real world scenario. For network analysis, let's say for network analysis, if you want to do some analysis for the data center, for XYZ, issue or whatever it may be. So how do we correlate this modular function to the real time? Mm-hmm. Oh, yeah.
Have like 100,000 nodes, you can work with this thing. But as soon as you go to couple of million nodes, like
Let's say
run
we have like 10,000
yeah,
devices.
10,000 nodes. So in that case, what matters a lot is how you model the network. Like what kind of metadata you are putting it on putting on the edges and the nodes.
Oh.
So like once you have a network problem,
Okay, just trying to understand.
Yeah.
Thank you.
Yeah,
Sure.
yeah. So let's do another exercise. So when people did this survey, they basically missed out 2 people. So let's add those people in this network, and how to do that is so basically you can go through the documentation of NetworkX out here, and the function is gadd node, which basically adds a node, and gadd edge adds an edge. So in this exercise, you have to add a new relationship between a male which is named 30 and a female which is named 31, and the other individual 7. Like these 3 people are besties. So like whenever you ask a question that who's your best friend, they'll be like, oh, 31, and 31 will be like, oh no, 30. And if you ask the same question to 7, so it's like a bestie triangle, and you have to model that. So basically, in this, you have to add nodes and add edges. And if you want to understand, if you have any doubt with the syntax, you can check out this thing here. You can check out the documentation of NetworkX, which introduces everything perfectly. And once you're done with this thing, thumbs up. Yep.
So if we didn't already have G instantiated, could we do this? Could we do like g.add nodes from scratch to create a network?
No.
Or
You need to instantiate the graph object. Then you can add whatever you want. But for example, you don't need to do you don't need to add nodes to add edges. Like suppose if you just did add edge 30, 31, count 3, it would add 30 and 31 as nodes, but it won't add the metadata gender. But you need to create a graph object first to manipulate that. Yep.
So I noticed that when you're adding the edges, it's unidirectional. Is there a bidirectional way to add edges?
Yes, there is. So just to show you that, if we do something, if we check the type of G, right, you see it's a directed graph. So it's like, digraph is directed graph. And in this case, if you want to add edges which are like, which goes both directions, you need to add an edge which is like, which goes from 1 to 2 and 2 to 1. But if you want to add edges which are without direction, there is something else called just a graph, and we look at those later. But in this, because
A nice API addition to NetworkX might be, if you want a PR, would be to automatically add bidirectional edges. So add bidirectional edge or something.
You have directional less edges and you have direction edges too, but no one could actually come to consensus how to implement this. So that is the problem right now. But if you want to go ahead, I think there's a PR open with hybrid. Asking questions to the ask three questions, the student will reply three times that this is my best friend. 1, 2, 3.
So the count thing basically comes from the way that the data were generated. So I noticed you talked about it as like a keyword argument to the add edge method, right? And so that what NetworkX does is it actually collects all of the keyword arguments that are passed into add edge, and it adds them as dictionary keys for the metadata. So count is not by no means like a fixed keyword argument. You can add anything you want.
So if you look at the signature of the function, it's like the starting edge, the end of edge, and just a like you can pass in any keyword you want, and that. Yeah. Yeah, it's a weight on the edges. Yeah.
Yes, and just a reminder, if you want to ask a question, please raise your hand, and I'll bring the mic over.
Thumbs up if you are done with this thing. Add node, add edge. Once you're done with that, verify that whatever you have done is right. And how do you do that? Wait, what? Because I didn't run this. Yep. People with the thumbs up, did you get all tests passed? So like this is the answer flashing on the screen. So it's again add node and add edges, and you can create a loop to do this too. Like you can create a permutation of 3 and shift between them if you are feeling fancy today. But I just did this, and let's just take a detour and actually look at the graph structure. So suppose I pass in. Because it's a dictionary, right? If you access dictionary, how do you do that? Let's use square brackets. If we do G1, you see you get this thing called Atlas view. Again, ignore view for the time being. You see that it's kind of a view of dictionaries, right? So once you pass in G1, 2, you have 1, right? Which is the which gives us the metadata of the edge 1, 2. Suppose I pass in 2, 1. In this case, there is a bidirectional edge, but like when you're talking about directed networks, suppose this thing exists, G12 exists, that does not necessarily mean that G21 will also exist. In this case, it exists, but that's just by incident. And again an API note. If you are using 2.0 and later, like both of these ways of accessing the weight or the attribute will work, but this is the oh yeah, sorry. But this is the more Pythonic way now. So if you're creating a new application which depends on NetworkX, so use this, because I'm pretty sure this wouldn't be deprecated in the future anytime soon. But if you are writing new code, use something like this, which is the new way of writing NetworkX code. So we won't do this exercise, but this is for break time. If you are done with your coffee fast, you can do this. So like the controversial part of this data set, right? So let's try to find out unrequited friendships. Like, I always say, oh, you are my best friend, but that person is like, no, sorry. So so basically that's like, you need to find these friendships, and you can do this later in the break. And and there are solutions too for this if you want to check out. And talking about tests, again, as Eric mentioned, tests are something which are used a lot in software engineering. They're like, do you have test-driven development and stuff? But there isn't enough there isn't enough momentum behind testing in data science. So it's always nice to have always test your data, not just your code and algorithm. Just test your data. Like if someone gives you data, just actually check it has what it says. So it can happen. You never know. Sorry. We'll have the break later. Yeah. Once we'll have the break. It's at 10:15, so it's like 25 minutes from now. So yeah, so this is iteration over list comprehensions. This is the Pythonic way of doing that. You can see this in your notebooks. So let's take a detour and talk about drawing graphs. So if we just try to plot our graph that we had, what do you see? Do you see this beautiful picture? What do you think of this beautiful picture? Yeah, chaos, spaghetti, or hairballs. So I mean, again, like you don't get, or you get some information about these. Like these are probably the 30, 31, and 7-1. That triplet of besties, but you don't get a lot of information from this standard pictorial representation of a network. And so the rule of thumb is that if you have 20, 25 sparsely connected node, like if you don't have a lot of connections, then you can have a picture like this, which actually gives you information about the network. But if you have 100 or even millions of nodes, you won't get a very good, you won't get a lot of information out of the visualization. So okay, so this just happened like last week. Someone tweeted that, oh, I need to visualize 20 million nodes and 80 million edges. I'm like, I mean, yeah, like, okay. So a lot of people are like, cool, nice. But if you just count the number of pixels in your screen, they're less than the number of nodes. So you can't really visualize it just by plotting it like this. You need to do something more. You need to do something with the data first and then visualize it. So like if you want to do that, if you have 20 or like a billion nodes, a very standard way is actually to compress the nodes into clusters of nodes and then try to represent the relationship between clusters. And I think we will discuss that later in the tutorial. So I mean, okay, this doesn't give you information. So you would argue, oh, because we don't know anything about the nodes. Let's even add the name of the nodes, right? Still doesn't give you anything except the bestie relationship. See, this will always be there. Doesn't matter your plot. So there are other ways of plotting a network. So one of them is the matrix plot, and this is my favorite plot because this comes from the representation of a network. A network can be represented by an adjacency matrix. People who have done computer science or maths, they'll know what I'm talking about. But if you don't know what an adjacency matrix is, it's like you create a matrix, and so this is our matrix. So if 1 is connected to 2, like these are numbered 0, these are number 1 to 29, 1 to 31 in our case, 1 to 31, 1, 2, 3, 4, 5, 6, 7, 8 till 31. And if 1 and 2 are connected, you'll have a number here. And so there is something in the matrix. And if they're not connected, you have zeros. So this is our matrix plot, which comes up from this. So can someone say anything about this matrix plot? Do you see anything interesting in this plot? No diagonal, yeah? What does that mean? Like, so diagonal is what? Like, yeah, so that's a good thing, right? So no student said, oh, I'm my best friend. So that's good, I guess. Our society still has hope, I guess. And any other thing that we can see from this matrix? Yes, it's not symmetrical. Because this is a directed graph, you're not guaranteed symmetry in a directed graph. But if it were a indirected graph, you would see that this matrix is always symmetrical. Like another thing that I like to do with this plot is, I mean, you can kind of create QR codes with this graphs, because like this looks like something like a QR code, right? So you can create random graphs, and using those random graphs, you can create random QRs. So if you want to, like, waste 2 hours of your life, try doing that. It's fun. And so let's talk about something called an arc plot. I mean, I don't use these plots a lot, but Eric swear by them. They're like, they look very nice. And I mean, come on, they do look very nice. So in this, the idea is that instead of worrying about just plotting nodes and just trying to draw edges, worry more about the position of nodes, like how nodes are positioned. And once you have that figured out, the edges will flow from that. So in this, you can see that you have first you have grouped nodes, like you have females and males grouped separately, and then they are also in a descending order of how connected the graph is. Like if you have a lot of different connections for a node, you are at the top of this chain. So if it gives you more information, especially than this hairball, right? You have more information, and you can actually go show this to people, and this is our graph, and this is what's happening here. And circus plot is arc plot, but joined. So, and again, this looks perfect, right? This looks, if you want to sell something, and so this is what you show. And yep, and all of these visualizations are not in NetworkX. NetworkX is the NetworkX is not a visualization library. They have an nx.draw, which does the work, but they're not a visualization library. There are other options. One of them is NXViz, which is written by Eric here, and it's a nice library if you want plots like this. And then there are, I think in the Python ecosystem, you can use Bokeh. You can use, I think even Dask has something now to visualize. No? Oh no. Oh yeah. They use PyGraphViz. So there's PyGraphViz. There's Bokeh. And if you're okay with moving out of the Python world, there's something called Gephi, which is used a lot by people at least in academia to make graphs. But again, this is one of my favorite plots. It's called a Hive plot, and it's really nice because it gives you relationships between the nodes in a group, and and relation between the group. So, for example, these are like male students, and these are also male students. This is just a copy of those students, and this is how they are connected inside the group. Like how males are connected to males, and this is how males are connected to females. And you'll see you have a bunch of popular fellas with the females, and you don't see that in female. Like it seems like it's evenly distributed all across females. So that's an interesting observation too. Yep. So let's now move to notebook 3. Yep. It's time. So it's 9:56. Breaks at 10:15. But yeah. Yeah. If the snacks are not out, we'll just introduce this notebook and then we'll go for snacks. So in this, we'll use data set from socio patterns. It was a added a chip to your to your lanyard or something, and you're just talking to people, right? So if you're talking to people for, I think it's for 30 seconds, there's an edge connected between them then. So this is how you created this network of people, like how people talk to each other, like how they interact in a room, how they interact in a conference or something. So that's how they created this data set. And so the idea is that how infections can spread through people. Like suppose if you say these are just hypotheticals. Suppose you say you need 30 seconds for a virus from person A to spread to person B. So like stay away and how to model that. So let's load in the data set and let's check what's there in the data set. So we have around 400 nodes in the data set and 2,700 edges. Now comes let's talk about analyzing the network. Till now we just had a look at the description of the network. How many nodes, how many edges, how do they look like. But this is where the fun begins now. How do we evaluate like important nodes? For example, in Twitter, right? Who do Elon Musk is important. Is he important? I don't know. Maybe he is. Any, but okay. Suppose we are just looking at the Twitter network itself, followers. Yeah. Like one way of looking at it is like just calculate the number of followers, right? So this person has 20 million followers. This person must be an important person, right? It makes sense. So like this is how this is how any sane person would say. If you go to a person who doesn't know what network science is and they're like, oh, who's the most important person on Twitter? Like, oh, just count the followers. Yeah, that makes sense. There's nothing wrong with that. So instead of followers, we count number of neighbors. So basically, neighbor is like the number of nodes a node is connected to. That's the neighbors. So let's just ranked importance, like we know that like one of the ways of calculating importance is calculating the number of followers or number of neighbors in our case. So let's create a ranked list of who is the most important node in this network. So we have this network G, which we know here, and we calculate the neighbors for, so basically the idea is to calculate the neighbors for every node and find the maximum of that. You do that, or the better way to be to get a ranked list. Who is the most important one? And once you are done, please give me a thumbs up. If someone's done, can someone tell me the answer? Who is the most important node in this network? 51. Okay. And okay, so we know what the network is. It's like it's how people interact in a conference. So what can we say about the node 51? What kind of person is node 51? Maybe, yeah, an extrovert, yeah. So, and in a case of a flu outbreak, what do you do with 51? You stay away from 51. Thumbs up if you're done. As you can see on the screen, I have the answers flashing up because again, there is no one way of doing it. So you can use like create a data frame and then try to figure this out, or you can use the sorted function to to solve this, and you can just use you can just create a list and then sort it. Like you can use whatever you fancy, and again there is no one right answer. So we used our basic approach of counting followers, right? Because that would make sense. Just count the total number of neighbors. Whichever has the highest one should be an important node or an important person in this network. So now let's talk something about degree centrality. Uh, Degree centrality is nothing just but a fancier name for a number of neighbors. So what it gives you is it gives you a normalized version of number of neighbors. So degree centrality is the number of nodes you are connected to divided by the number of nodes you can connect to. So suppose you have 100 nodes in a network. How many nodes can I connect to? Anyone? Sorry? I have 100 nodes in a network. How many nodes can I connect to? 99, yes. Assuming we don't allow for self loops, right? We don't have any narcissist in our this thing that they'll just talk to themselves like, oh yeah. So we have so we have that number n minus 1, right? That's the denominator, and we know the numerator is the number of nodes you are connected to, which is like whatever the number of nodes you are connected to. So again, like degree centrality is just a fancy way of saying count the total number of neighbors, and it will give you a normalized version. And if you sum everything, you'll get 1. If you sum all the degree centralities, you'll get 1. Yeah, you should, yeah. And so to do that, again, NetworkX gives us a nice little function called nx.degree centrality. You pass in a graph. It will give you a nice looking dictionary which is keyed by the node, and a nice little float which is the degree centrality. So if we just look at any 5, we get this thing. So I don't think we'll do this exercise after the break. But does anyone know what is ECDF? Anyone can tell me?
Testing. My favorite chart, the empirical cumulative distribution function, I think, just shows you like. I love that chart.
Eric loves that too. So instead of using histograms, you can use something called an ECDF. It's not a very obscure concept, but not a lot of people use it. And apparently, a lot of people should use it. So we will do this exercise later. But in this exercise, you have to calculate the. You can start right now, and then you can go for a break and come back. You have to create an ECDF of the distribution of degree centrality and of number of neighbors, and then just compare the plots of these two and make sure that it's an actual straight line, because as I said, degree centrality is exactly what number of neighbors is. So you should end up with something like this, a plot for degree centrality versus number of neighbors. Yes. Yeah.
Could you just real quick explain the whole it has to sum up to 0 thing? Because it doesn't seem intuitive to me. Like if you and I are both best friends with
Yeah.
90% of people in the room, I don't understand how the degree centrality would sum to 1 conceptually.
Okay, suppose n minus 1. N minus 1 is our base, right? If I'm friends with you, if everyone is friends with n minus 1, I think it wouldn't. Oh, sorry. It wouldn't. It wouldn't sum up to 1. It shouldn't sum up to 1. And wait. I need to think about this. So yeah, we can talk about this in the break, and I think we can take the break now. Yep, yep. So I think we meet at 10:20, 10:25. Okay, so let's be back by 10:25, and if you come back early, just start working on the exercise.
There's snacks out there, so
Yeah.
have fun.
break back. I hope you had a good snack and coffee break. So you can start working on this exercise. And if you're not very familiar with Matplotlib, it's okay. Just like open the instructor notebook and you can get what's happening here. You need to be familiar with Matplotlib for this exercise. And once you're done, give me a thumbs up. And this is what you should end up with. A plot looking like this for degree centrality, a very similar plot for number of neighbors, and this straight line plot.
Somebody mentioned that you use these instead of histograms. I vaguely remember this in college. Is it if it's straighter, the line, the more normally distributed it is, or no? Okay. How do you read this? I imagine you'll probably get into it.
Okay, I'm going to do my spiel on ECDFs, okay? All right. ECDFs are really cool because they tell you more information than a histogram. You can read off much, much more information than you can from a histogram. The only thing is that people are not used to it. That's it, okay? So let me give a bit of a demo, okay? We got this ECDF up here. On the x-axis, you have values that your data points take on. And on the y-axis, we're showing the cumulative number of points that are smaller than any particular value inside the data set, okay? So a number of things are immediately, like you can read it off. You can read off the median. If you draw a line from the 50th percentile over onto the curve or the dots, and then you project back down, you can see what the median is straight away. And because you can read off percentiles so easily, you can read off interquartile ranges. You can read off the 25th to 75th percentile very easily. You can even read off like the minimum and maximum pretty easily. So actually, Mriddle, can you change this to plt.hist? So, and I think it's just degree centralities, just plt.list hist degree centralities. Misspelled degree.
Whoopsie. What?
It probably needs to be run first.
Yeah. Oh yeah. Whoops.
Try reading off the median from there. Try reading off the interquartile range from there. You can't. One of the big problems about histograms is you have binning bias. If you change bins to like that, suddenly, yeah, we got like 3 outliers, potentially 3 outliers. But did we know that if we use the default settings? No. Do people change default settings? No, sometimes, no, not rarely. Yeah, you get something like this. Now, what's going on there, right? Use an ECDF, like, all right, and bring it back to your institutions. Like, ECDFs give you the same information as a histogram, just richer. Just richer. And in fact, bimodality is what some people are used to looking at, 2 humps in the data set. If you've got strong bimodality, you'll see that inside an ECDF in that you'll see a middle plateau and then a second plateau. If you have trimodality, you'll see 3 plateaus. If you can't see plateaus, you don't have bimodality no matter what your histogram says. Okay? Cool? All right.
And coming back to the normal thing, if you have a normal distribution, you'll get a perfect S. A perfect S, which, and a perfect, like, bimodal, you have like perfect S with a.
Of the degree centralities, is it the same deal where you should expect an S for normality or no?
So if you simply log transform the x values, that still might not necessarily get you to normality. We can try.
No,
But-
for normality, like
It-
if you have a normally distributed degree, the log plot will also be a normally distributed degree. And if you have an exponential decay, then you'll get a straight line. That's
What are the purposes of doing the log of this?
so at least like the log plot is so basically. I think what the reason was is so there was this theory of a preferential of how networks grow, how how the degree is distributed all around the network, and that followed a decaying power law, which is just a decaying exponential function. And if you take the log plot of that, you get a straight line. So it's just I think the idea comes up from it's a test. If you get a straight line in a log plot, it's a scale-free network. So I think we'll discuss that for a bit later. So this is what you should get in the plot, and let's just discuss this plot for a bit. As Eric mentioned, the 50th percentile. So 50th percentile goes to 0.03. So we can say that the degree centrality of 50% of the nodes is less than 0.03. Then if we go up, the degree centrality of 0.95, 95% of the nodes is less than 0.08. So we are getting we're getting something here. 95% of the nodes are very sparsely connected. They're not connected to a lot of other people because they have a very low degree centrality. And you have these 3 not outliers exactly, but you have these 3 people in this network which are connected to a lot of other people. So what does this tell us about a real world? Does this mirror your expectations? For example, in Twitter, right? You don't have not everyone has 20 or 30 million followers. Majority of the people would have 100 or 200 followers, but you will have these three people are I don't know. I think Shakira has the most followers. Who has the most followers? I don't know. I know a female pop artist has the most number of followers on Twitter. So these are those artists. No. Kardashian is it's a US thing, thankfully. Yeah. So if you look at the degree centrality ECDF and the number of neighbors ECDF, it looks similar, but it's not just similar. It's the exact same plot because the degree centrality is just a normalized version of number of neighbors. And if you would plot the XY plot, you'll get a straight line. The relationship between degree centrality and number of neighbors. This is as expected. So this is an exercise, but we won't do this. Let's just look at the Circos plot of this, and now we'll see why having a plot like this makes sense. So for the first thought of this picture, this looks like a nice, pretty picture, right? Yeah, everything works. And if you look at these are the nodes because this is a Circos plots, And this represents the incoming time because this is an event, right? And we have information about when every node or every person enters into this conference. So like it goes in an anti-clockwise direction. This is increasing time. Like this bar is increasing time. So what can we infer from this? Anyone? This is a plot between between interactions. These are the nodes in a these are the nodes with an increasing time order. Can we infer anything? Look at this space in the middle. What can we infer from this?
It looks like people like lunchtime because you got a lot of activity. I mean, I assume this is one day, so it just
yeah.
what I see is that at the beginning there's not as many, at the very end there's not as many because that's like the left-hand side.
Not as many. What?
It's not as dark, which I assume
okay.
is representative of the number of interactions.
okay.
You see a lot more on the far right.
Okay, but so like let me make that clear again. So this is node 3, which enters at a certain time. This is suppose node 20, which enters at a certain time. If there is a link between them, it means they had an interaction. Like you're like okay, that makes sense. You know, people if it's darker, people are interacting more. That's perfect. But there is another interesting thing that we can take out of this plot. Yeah.
So that people are mostly interacting with people who came in at a very similar time.
Yes. As you can see, like if you come at 8 a.m., you are just interacting with the people who came in. I think this interaction goes up to maybe like 10 or 12. So you are interacting with the people who came in at a similar time as you. So you, if that wasn't the case, you would see a lot of connections in this middle. So this is one of the reasons, like choosing a correct visualization is important. Like if you just plotted this on our nx.dra, like well, good luck with that.
Try inferring that from a hairball.
Good luck with that. So this is again one of the reasons why visualization is important, and choosing the right visualization is important. So let's move on to another concept in network science or graph theory is paths. And in my opinion, this is one of the most useful and one of the most important part of networks is graph traversal. Like suppose suppose talking about this socio-pattern network, suppose I tell a person X something. How much time will it take to how does things spread in this network, right? If I know the path from this person to every other person in the network, I can try to model these things, right? So this is one of the reasons graph traversal is important. I mean, even Google Maps that I assume a lot of people use here is a basic problem of graph traversal. And you can actually create your own Google Maps in a Jupyter notebook. If you want to know that, meet me after the tutorial. I was kind of working on that. So let's talk about shortest path. Going from point A to point B, there are multiple paths possible, right? But one thing that we are very interested in is finding the shortest path, because that's sometimes a good thing, and sometimes we are not, but sometimes that is what we are interested in. And if you remember from your college days, or assuming if you have done computer science or maths, there is something called BFS, breadth first search, and depth first search. These are standard algorithms to find the shortest path in a network. So the basic idea is that suppose I want to find the shortest path between me and let's suppose we are in the Facebook social network, right? Where every node is a user. Like I'm a user of Facebook, so I'm a node in the Facebook social network, and every friendship is an edge. So suppose I want to find the shortest path from me to Mark Zuckerberg, right? So basically I'll start jumping. So I look into my neighborhood. I look to my friends. I go to every neighborhood and then ask, are you friends with Mark Zuckerberg? Are you friends with Mark Zuckerberg? Are you friends with I do this for all of my friends. if I don't get a answer yes, then I'll jump in my friends of friends, assuming I have access to all that data. Then I'll ask everyone. So basically, you keep on expanding your neighborhood search with degree 1, degree 2. But in this case, I mean how far I'm going from my initial set, and this is how you find your like this is how I find the shortest path between me and Zuckerberg on Facebook. So we're talking about this. Does anyone know about 6 degrees of separation? As in, can someone tell me that? Yeah. Yeah. Who was? I think yeah.
It's the concept that if you have any two people, they should be connected by at least like through a path of 6.
Yeah. So I think it was some sociologist came up with this in like 80s or 90s, that it's called the small world theory, that we live in a very small world, that I can jump from one person to any other person in this world in less than 6 steps on average, and on average being the keyword term here. So I think so Facebook is the largest known social network of the world, right, where like there is a concept of friendship and knowing each other. So I think they ran this couple of years back when they had 1.3, 1.6 billion people, and they found out the average shortest path, like the degrees of separation is 3.8 on Facebook. So, and that's a very interesting fact, right? That within 4 jumps, like within 3.8 jumps, I can reach anyone on Facebook. Like if I'm friends with you, you are friends with someone else. In this, like just in like 4 jumps, I can reach to anyone in Facebook, and Facebook has 1.6 billion people at that time. And when they did this, they actually released a tool where you could see your personal like not just average, your personal shortest path length. So that if I am here, like how many jumps will it take? And I think for me it was 3.9, and for Zuckerberg it was 3.1. So I mean, I'm pretty. It's not 3.1 for him. It's 1, but that's a different story. But they have removed that tool now. So, oops, you can't use that anymore. So coming back to shortest path. So this is the basic idea behind BFS2. In BFS, it's called breadth first search. So in this, you suppose you are a node. You start looking at the neighbors of the node. Does my destination exist in the neighborhood? If no, then I look at the neighborhood of every node in my neighborhood. And you just keep on doing that. If you implement this, you can implement this in a recursive way. And like it's an exercise in the notebook, but we won't do it because it can take a lot of time. So let's just go through that. And the funny thing is, the thing that we asked you to implement in the notebook is already present in NetworkX. So we don't actually need to do that. So suppose you want to find that is there a path between node 400 and node 1? It gives you true. This does not necessarily mean that 400 is connected to 1. This means that there is a way of going from 400 to 1 somehow. By jumping around the network, you can reach 1 from 400. And suppose you want to find that path. How do I reach from 400? How do I reach to 1 from 400? You just run this little algorithm. Not an algorithm. You just call this function shortest path. And if you're familiar with graph theory and like graph algorithms, you would know like there are not tens, but there are a lot of different algorithms to choose how to find the shortest path. There is BFS, DFS, Dijkstra, A star. There are a lot of algorithms, and if you call shortest path, NetworkX will take care of finding the most efficient algorithm for your graph and for your use case. And there's nothing fancy going on behind. These are a bunch of heuristic that just always work. So you don't need to worry about that. If you don't really care about the implementation, just use shortest path, and you'll get the shortest path from node 1 to 400 in this case. Yes.
how would you figure out what algorithm it's using to get the shortest path?
I think, for example, the heuristic is that if it's a simple graph, which you have no weights, no nothing, like just nodes and this thing, you use BFS or DFS. And if you have weights, you start using Dijkstra. If you have negative weights, you have A star. So it's just like, it will use the simplest algorithm for your graph. If as soon as you start complicating your graph, it will use a more complicated algorithm. That's
What is DFS?
DFS is so breadth first search is like looking into your neighborhood. In DFS, you go into one way. I look at one of my friends, and then I look at his or her friends, and I just keep on going in one direction until I reach an end. And if that end is not my destination, then I retract back. So that's the idea of DFS. You go depth first, and in breadth, you just swim around your neighborhood. I mean, if you want to, you can implement this exercise after the tutorial to get a better understanding of BFS. So, but let's do this exercise instead. So in this, you have to write a function that extracts the shortest path. So we know that this function nx.shortest path gives us the graph, right? It gives us the path, sorry. It gives us the path that going from 1 to 400, I need to take this route. I jump from 1 to 50, 50 to 188, to 230 to 335, and I reach my destination 400. Now you need to create a new graph which has just this path. And how to do that? Use this command, g.subgraph. If you pass in a number of, if you pass in a set of nodes, g.subgraph will extract those nodes and its relationship and give you a new graph. And once you're done, just give me a thumbs up. And if you're done, try to plot it too. Like you should get something like this. Try to plot that graph. Thumbs up if you're done. Yep.
Thanks. Is there a reason that running this multiple times gives you different looking graphs each time you run it?
No, it's supposed to do that. Whenever you call nx.draw, it will give you a randomly drawn picture. If you want to fix it, you need to, there are other arguments in the function that you can give in, which gives you a fixed answer every time. But the picture is drawn randomly. So you should get different pictures. So if you look at this, if you can look at the solution which is flashing on the screen, we have this check here. Is it possible to have, is it possible that there is no path in the graph? If yes, then when? Anyone? When is it possible to not have any path in the graph? When does that happen?
If your graph is disconnected and
Yep.
they come from two different sections.
Yep. So it's very much possible that your graph is not connected. We will talk about this later too, and so that's why we have this check. So if there is a path, then create a new graph. Otherwise, let's raise an exception. And if you look at this is our plot, it looks like a straight line. Is it possible to have a different plot for this subgraph? Is it possible to have something like you have this line graph and then there is a connection between 90 to 230? Is it possible?
Not when you're grabbing the shortest path.
Yes. If you are grabbing the shortest path, then as soon as if you have a connection between 90 and 230, it will end up taking 490 230 rather than going all the way. So this is the only possible answer for this subgraph, and this is, if you want to give a name of this, so it's called a line graph, which is basically a line. So it's called a line graph. So again, there are more exercises that you can do at home. So in this, we basically we create a star graph, in which we basically look at the neighbors of the graph. And there are more exercises for home. So let's go back to hubs and the notion of what is important, what is not important. We just mentioned one thing, right? Like degree centrality on neighbors. Just look at the number of neighbors, and if the highest number of neighbors is the most important node, that is what we concluded, right? But it's very much possible that that is not the right way of measuring importance. So can someone think of a way where just by looking at the number of neighbors, it's not the best way of measuring importance? What could be any other way of measuring importance in a network?
Like if you have distinct groups and you had people that connect those groups, so they serve as, bridging the gap between two otherwise pretty segmented communities, I'd imagine that'd be an important person.
Yes, exactly. So it's like if there are bottlenecks in the graph, like suppose there are 3 different groups in a network, and you have only one node in the network which actually connects to all these groups, even though that node is connected to only 3 different nodes, but it connects the whole graph together. In that case, it's an important node. You can count it as an important node. And the funny thing is that there is no, whenever someone asks me, oh, how do you measure importance? There is no right answer for that. It depends what you are trying to measure. For example, if you're trying to measure the, which is the bottleneck in a node, it has a different answer. If you want to just measure how to spread things in a network, then degree centrality is one of the basic ways of, measuring that importance. So we look into something called betweenness centrality. And the intuitive definition of betweenness centrality is that I start finding shortest path between all the pairs of nodes in a network. So I find shortest path for every node, for every pair of nodes in a network, and then I try to find the node through which most of these paths go through. Does this make sense? I try to find a node through which most of the shortest path in a network go through, and which is basically the bottleneck. Like every shortest path in the network has to go through that node. Not every, but most of the shortest path have to go through that node. And basically you try to find these nodes, and as soon as you have these nodes, these are the most important nodes. To give you a better picture, we'll look at that later. But before that, let's see how degree centrality and betweenness centrality interplay. Like, can we say anything about a network? Suppose a node has high degree centrality. Can we infer anything about the betweenness centrality using the degree centrality? Any guesses? Should we be able to infer degree centrality from betweenness centrality? Any guesses? Yes, no. Let's see. So in this exercise, you basically plot in this we plot the degree centrality versus betweenness centrality plot, and as you see, you can't really say anything about how they are related. Like for example, this node has very high degree centrality, but has very low betweenness centrality. That's the whole point. The way we are calculating these centrality measures, they are very, very different. They're very different. So we can't infer degree centrality from betweenness centrality or the other way around. So, I mean, I think you can, if you try to make a network, you can probably make a network which gives you a straight line, which is like, degree centrality is always related to betweenness centrality, but you have to over-engineer that network to give you that result. But in the real world examples, you won't find that, you won't really find that. Yep. So coming back to how, how you find bottlenecks, can we, can you come up with an example where a node has very low degree centrality, but very high betweenness centrality? What would that example look like? Anyone? How would that example look like?
I would imagine that it would be like a node that connects two clusters of, or two clusters of nodes.
Yeah, exactly, something like this, right?
Yep.
Yeah, so in this case, like if you measure degree centrality and say, oh, you want to find the most important node, you find the degree centrality and that's our final order. But according to degree centrality, these two nodes will be the most important nodes because they have the most number of connections. But according to betweenness centrality, this node will be the most important node, even though it has only two neighbors. But every path, if you want to go from this cluster to this cluster, you have to pass through this, right? So if you remove this fella right here, you break apart the network. Yeah.
But doesn't every one of those paths also have to go through the one on the edge of the top left and the one on the edge of the bottom right? Like, wouldn't those three middle ones all have the same betweenness
Wait,
centrality?
no, that
No.
wouldn't, because like, for example, if you start a network from here, it will have that network too, right? If you want to go from here to here, then you have,
Oh,
in the
okay.
calculation, it will end up adding those those
I
paths
gotcha.
too.
Cool, thanks.
And so funnily enough, so like in the 8th notebook, that notebook is about US airports data set and like, how airports are connected. And if you run the standard algorithms, which is the most important airport in this data set, if you run betweenness centrality, you get a very interesting result as the most important airport. Can anyone take a guess which is the most important airport in the US airport directory? Like New York? No? Yeah, like these are the usual guesses that you would make, but no. According to betweenness centrality, if you look at just the structure of the network, again, I'm emphasizing on structure. I'm not emphasizing on number of people, number of number of flights, anything. If you just look at the structure of the network, Anchorage, Alaska, is the most important node in the network. And if you want to find an answer for that, I don't think we will be able to cover that in this. We don't have 2 parts this time. So you can talk to me later, or you can just look at the 8th notebook. You'll have your answers, what's happening there, why Anchorage is the most important airport. So moving on to the, before we move on, any questions, any doubts, any comments? Okay, let's.
Is there a question back there?
Sorry, I just wanted to make sure I understand. So this algorithm is based on shortest path?
Yes.
So if the graph was weighted, it's not the number of nodes, it's the shortest path?
Yes, yeah.
Okay.
And okay, you bring in an interesting question. So again, now this depends. When you're measuring shortest path, how do you define that weight, right? Sometimes, for example, in the case of airports, right? When you recreate this network, like should the number of flights be equal to, suppose you have number of flights as a weight, should we use the weights just like that? Because suppose if there are 100 flights from New York to Chicago, and there are 100 flights from Chicago to San Francisco, like you have 100 flights because these are important routes, right? And you have only 20 flights from maybe New York to Anchorage or something. So if we use standard shortest path algorithms, it will penalize routes like New York, Chicago, and Chicago, San Francisco, because you're giving it high weights. So a way to counter that is to use like an invert. You need to make sure that you are modeling your network correctly. Otherwise, you'll end up with very wrong results. So like when you're adding weights, things get tricky. So like we need to keep a lot of other things in mind. So thanks for pointing that out. So let's move to notebook number 4, I think, yeah, 4. So till now we were talking about nodes, nodes individually. Now in this notebook we'll look at something else. We'll look at the structure of a network, where we're not really talking about just one node. We're trying to find local structures. Like, is there any interesting thing happening if you look at a cluster of nodes or something like that? We'll talk about that. So in this, we work with a data set of the Physician Trust Network. So I think these are 5 different cities, no, four different towns in Illinois. And this is a trust network between physicians, and it was taken in 1966. So it's like if you go to a physician and they're like, oh, if you want some advice or if you want to refer someone, who do you refer to? So that's how this network is created. And you have this result for 4 different cities. And let's create a plot of that. Can we, like, we have the data, we made a plot. What can we say about this plot? We know that it's from 4 different cities. Do we see anything happening here?
Oh, hold on. Where's the comment from?
How do you tell which cities are present in the visual?
That's part of the game. You don't need to know that. You just need to infer what's happening. Like if you look at the structure of this, is there anything special in the structure of this plot?
So it looks like you can almost see the four distinct cities
Yes.
with a very large city being on the very bottom with the well interconnectedness, and then you can see minor gaps between the other ones.
Yep. I guess that's the correct inference from this, because you can see like 4 different clusters of cities. I guess because it was 1966, like communication wasn't that easy. People I think like a family doctor is a more intimate thing. So you won't just randomly say, oh no, go talk to that doctor in that town. So you see that these the trust networks are localized to cities. So that is what we can infer just from putting it out there. And again, if we plotted the hairball, you wouldn't see anything here. But with the circus plot, we can see a clear representation of that. So let's talk about structures in a graph. Before structures, let's talk about something called cliques. So in a clique, everyone is connected to each other. It's like an exclusive group or sort of thing. What is the simplest clique you can think of in a network where everyone is connected to each other? You just have to pick a set of nodes, and everyone is connected to each other. Which is the simplest clique? Sorry?
Family?
Yeah, family. Yeah, family is the right answer, but I'm talking in the sense of networks. Like you have nodes and edges, which is the most simple clique.
Just like 2 people that are connected to just each other?
Yes, like an edge. Just an edge is a clique because there are 2 people and both are connected to each other. What is the most simple complex clique? Anyone?
Three people?
And how would that work out?
A triangle.
Yes, I was looking for the word triangle. So you would see there are triangle formings, and basically you can build every clique with triangles. Like if you look at if you're looking at 4 people and all of them are connected to each other, it's basically a set of 1, 2, 3 different triangles. 4, yeah, 4, yeah, 3. It's a set of 4 different triangles, right? So you can build up like the nth clique with triangles. So that's why we focus on triangles, and because finding triangles is still a hard problem, but I think finding maximal cliques is a NP hard problem. So we won't talk about that. So in this piece of code, what we have implemented is that if given a graph and given a node, it returns that is that node in a triangle. What does that mean? So basically, I give you a node, and I look at the neighbors of this node. And once I look at the neighbors of the node, and I look, do they have a connection? If 2 of my neighbors have an edge between them, we're in a triangle relationship, right? Make sense? And NetworkX gives us a function to calculate the number of triangles. So this means that node 3 is in 3 triangular relationships. Node 1 is also in 3. Node 2 is also, apparently all the nodes are in a 3 triangular relationship. So exercise time again. So in this exercise, you have to write a function that takes in a node, that takes in the graph, and it returns the list of all the other nodes it's in a triangular relationship with. Which one is this? Thank you. just to give you a better intuition again, you start with a node, you just look at all of its neighbors, and you try to find if there are any two neighbors which have an edge. As soon as you have that, you have a triangle. Thumbs up if you're done. So if you look at the answer flashing on the screen, it's again, we check for every neighbor, we run through it combinations, and we get a combination of two pairs of all the neighbors, and we check if that pair has a edge between them, and if yes, then we add it to the triangular set, these triangular nodes. And just to show it pictorially how it works, so in this case, like 3 is in a triangular relationship with 42, 60, 67, 41, 9, and 11. And just to make sure that our answer is right, we also plot all the neighbors. So if you see that these are all the neighbors of node 3, and only these are the triangular relationships, and we get those relationships. So that means, yeah, our code was right. So like, let's talk about a nice important application of these triangles. It's friend recommendation. this is, I'm pretty sure it's much more involved than like, just solving open triangles. But this was the first implementation of recommendations in LinkedIn. For that, I think that we know. I'm not sure about Facebook how they do it, but this is a way of understanding how recommendations work. And so suppose you have an open triangle. And what do I mean by open triangle? Suppose I have two nodes, I have two neighbors, and they're not connected to each other. Maybe they should be. That's the recommendation we're talking about. Like suppose I have three friends, right? And they're not friends with each other, but they're friends with me. So there is a slight chance that they know each other, right? So that's the recommendation, that maybe these three people also know each other. So that's a very basic recommendation algorithm that you can come up with of how to recommend people in a network. So in this exercise, you have to write a function that identifies the other two nodes which are in an open triangle relationship. And in this exercise, you just have to consider the one in which you are the central node. Because it's possible that, suppose I'm friends with X and X is friends with Y. So you don't have to return that, no, I can be friends with Y. You don't have to return that, in which you are the central node and there are two friends. You have to find these open triangles. And the implementation is very similar to the one in which we are finding triangles. In the triangles one, we were finding which two nodes are connected. And in this, we have to find which two nodes are not connected, because they should be possibly connected. That's our recommendation algorithm. Again, once you're done, thumbs up. Thumbs up if you're done. So if you look at the code flashing on the screen, instead of looking for edges, instead of looking for nodes which have an edge between them, we look for nodes which don't have an edge between them, and then we add it to our recommendation pile. So if you look at this thing, so like going back to the data, to the data itself, it means that node 3 interacted with 1 and 9, right? And node 3 interacted with all these other nodes. So if node 3 interacted with node 1 and 9, so maybe there would be, you can go to node 1 and say, go talk to node 9. Maybe you'll have something in common. Like, no, not very sophisticated way, but maybe it may work. You never know. So let's quickly talk about cliques. So again, finding cliques is a very hard problem. So in this, like when you use this function called find cliques, it will give you all the cliques in a graph. It will give you 2 cliques, which are basically like, every edge. And it will give you, like, if you have 4 nodes in a clique, that means that every node is connected to every other node in the graph. So just to give you a better picture of that, if you look at, this is a clique, this is a 4 clique, this is a 6 clique, where every node is connected to each other, and it's called a complete graph in graph theory. So we won't do this exercise, but in this exercise we basically write a function to find the maximal clique. You pass in a size, and I want cliques of only that size. Yep. Now let's talk about connected. Yep.
I think there's one really neat point about cliques. If you have a 5 clique, it is exactly decomposable into all of its constituent 4 cliques, which are exactly decomposable into their constituent triangles, which are exactly decomposable into their constituent edges. So all triangles can be described as a set of edges. All 4 cliques can be described as a set, can be decomposed into their 3 cliques. And so all k cliques can be decomposed into their k-1 cliques down to k equals 3, where the k-1 clique is 2, right? Yeah.
And building up on top of that, this is one of the ways of aggregating information in a network. Suppose you have a very big network and you want to visualize that, right? You instead of printing out every node, you try to find these. Like suppose there are cliques, there are a lot of cliques in a network. You take that clique, like create a meta node of that clique, and then you plot out the network. So it's one of the ways of aggregating data to find cliques. And talking about different aggregations, going back to the case where it's not possible to find a path, right? Like you cannot go from node A to node B. And that's where connected components come into the picture. So components are these different clusters in a graph in which you cannot go from one cluster to another because they're not connected. And let's try to find connected components in our graph G. Whoops. This is not the, this is the physician network. I was still thinking about the conference network. So this is our physician network. And we see that there are 4 different components. And this is what we expected, right? There are 4 different cities in the network, in the data set. And every city is a network in itself. Like they don't communicate between cities. So if you try to plot this out, I mean, as you saw in the Circos plot, you have 4 different parts of a network. So again, in this we do the same Circos plot, but we add the notion of what the city is. And once we have that city, we see that the bottom half was our one city. Then we have different colors to signify that. So this is a prettier Circos plot of the same data. And yes, and this is the interaction between Democrats and Republicans through the years. So 1949, 1951. So let's go to 2011. So what can we say about the betweenness centrality of these people? So remember? Yes. So who is the most important like member of, no, not member of parliament, that's a British thing. Member of House of Senator, US Senator. Who's the most important US Senator according to this network and what we know about network science? Anyone? Who's the most US important senator? Like, yep. But again, depends how you define importance, right? Like in this case, suppose we are defining importance, who can get things done. Maybe someone who has connections in both sides of the house. So like you will need someone who is somewhere in the middle, and that person will have a very high betweenness centrality. So see, this is one of the real world use cases of network science. How to get politics working. Yeah. Eric, he has a question.
If you look at like some of the charts, like further up, like 1973,
yep.
There are a couple Republicans that are so far left that they're. What does that mean? Does that mean they're more connected with all Democrats than most Democrats? Like, how do we interpret some red that's penetrating super far to the left, or some blue that's penetrating really far to the right in the network?
I'm not sure. Do you know the answer for that?
Yeah. So. Part of this is how we've chosen to visualize the network. Or not we, but more like New York Times. Okay, so this is one of those classic hairballs, and if I'm intuiting it correctly, this hairball is drawn by a force-directed layout, so that if you have an edge between two nodes, there is an attractive force, and if you're not connected, there's a repulsive force. And the effect that a force-directed layout has is things like this and things like that can be visualized very clearly. So and also the other part is, just so that this is clear, the X-Y positioning of nodes in a force-directed layout carries no meaning. There is no meaning here. So it is by convention that red is put to the right and blue is to the left in US politics. That might be flipped in another country. And that is just an artifact of how, you just drag the nodes over, the red nodes over, and the rest of it will follow, and you drag some blue ones over to the left, and the rest will follow. And then, okay, now we roughly have them in some orientation that an ordinary person would be familiar with. So that I want to make very clear. The XY positioning in this chart inherently only carries meaning because someone decided that red and republicanism and right are put together, and left and Democrats and left, are put together, okay? Blue. So now you'll notice that, yes, you've got some of those red nodes that are right in the middle and of the divide between the two, and the same goes for the blue nodes. Now, if we were to look at it graph theoretically, thankfully, in a force-directed layout, they will match up with our intuition. So we will have some of these more bipartisanal kind of senators, or some representatives, if this was the House of Reps instead. Or if we're in the British Parliament, then members of Parliament, right? People who bridge different political parties as colored by the color that's attached to their nodes. The force-directed layout can help us discover it. I still, though, would have a preference for making sure that we quantify explicitly how many same group connections I have versus other group connections I have as a node. And that is the clearest way of computing how many, that's the clearest way of computing the bipartisanal or multi-partisanal metric. And yeah, it's good to visualize it this way, but I think there might be better ways to do it, right? Like you can do things like you can put you can do this, the arc plot as an option, where you have or rather, sorry, it's not the arc plot.
The hive plot.
The hive plot, yes, you have the hive plots. And let's say you have 3 political parties, like Canada should, right? Like 3, I'm Canadian, so. you have three major political parties. You put them each on the axis. You clone the axis for intra-group, and then you plot the inter-group between the two, right? And so then that's a much more rational way, I think, of visualizing this. And then you can compute the metric, the bi or multi-partisanal metric, and order nodes according to how many times they vote together with a member of another party, right? You can order it that way. And that's another great, like, yeah, so it's a better way, I think, of visualizing than a hairball.
Yep. So we have 50 more minutes. And so we have been talking a lot about, like, what are networks, what are cliques, what are paths, so basically we've been talking a lot about the theory, right? So let's see a real world example of that. Let's talk about, why this is useful. And I'm going to give you a very nice reason for that. The reason network science is useful is because we can understand Game of Thrones better. And so how many of you, like Game of Thrones? Okay, disappointing number, but that's okay. How many of you don't care about Game of Thrones? Well, that's okay too. But you have to sit through this. So Game of Thrones is the 7th notebook. Again, if you want to do the exercise, you open the student one. If you want to do if you don't want to do exercise, you open the instructor one. So even if you're not a fan of Game of Thrones, has anyone ever seen this picture before? Anyone? So in this picture, again, so people who are not familiar with Game of Thrones, what Game of Thrones is, it's a TV show which is based on a set of books, and it goes through a fictional fantasy world where people are fighting each other for, for the ultimate, who becomes the king or the queen, or I don't know, or yeah, it's cool, yeah, maybe. So in this network, this is the interaction network between characters. Like all these names are characters on the TV show and in the book. And so the bigger the font of a node, like for example, Jon, Daenerys, Tyrion, it means the more important that node is. And in this case, they have calculated importance not by degree, not by betweenness, but something called page rank. Does anyone know what is page rank? Has anyone heard about page rank before? Yes. So page rank is known as the $1 billion algorithm. It's behind Google's, it was behind the first Google search index, and it's named after Larry Page and web page. See, everything worked out there. And so bigger the font, higher the page rank. And if the colors you see in this are communities in the network. We haven't talked about what are communities, but just to give you a basic intuition, it's kind of like weak components, weak connected components. It's like you don't have a clear-cut difference between different components. There could be some edges between component 1 to component 2, but this is a basic intuition behind communities. It's like you can, force them apart somehow. And if you're familiar with Game of Thrones, you'll see that you have these communities, like you have this purple-looking community of people who are close to Jon Snow, as others would know him. And you have Daenerys, and you have her community. So you have you have this nice pictorial representation of how things work in Game of Thrones. And this is based on the books. So apparently there are enough differences to make a difference in this final representation. And I think this is from book 1. Yeah. So in this notebook, we'll go through book 1, book 2, book 3, book 4, and book 5, because we have only 5 books till now. And we'll see that how the notion of importance has changed. Like, can we predict that, not predict, but can we say who's the most important character in Game of Thrones? Like, who should win this battle? And if you are behind Game of Thrones and you actually like Game of Thrones, I'll make sure that there are no spoilers. But again, no guarantees. But I've tried hard enough to make sure that there are no spoilers. So let's start. So we read in, let's have a look at the data. So in this, this is a pandas data frame, and so you have a source, you have a target, you have this type thing, and you have a weight and a book. The type is a pretty much useless column in this, because all the networks are undirected in this network, and even source and target does not make sense in an undirected network, because it's not a source going towards the target, because the connection goes both ways, because it's an undirected network. And the weight comes into the picture. Weight is the number of interactions in that book. So, and the way they define interactions is if two characters are in a neighborhood of 15 words. This is created from the book, not from the TV show. If two characters are in a neighborhood of 15 words, like their name is mentioned, then there's an edge between them. This is not the best way of making it. I'm not even saying this, but this is a okay enough way of making it to get some actual results. And we'll see that this actually works of creating a character network. So let's create 5 different graphs, one for each book. So we have, yep, this question.
Wanted to seize on this real quick because we're looking at the base data. A lot of us are going to have super unclean data that's not already packaged in network formats.
Yeah.
Is there a best practice that you recommend when you're trying to just create a network from scratch? And is it like, if it's directed, then this is what the data structure should look like, and if it's undirected, then this is what it should look like?
I mean, it depends on your. It depends how you're modeling your system, right? If you know that there is direction in the system, then you just create the object directed graph. You use directed graph instead of using graph. If you know that there's no notion of directions in your system, then you create a normal graph. And the topic of data cleaning, right? In every data science problem, 90% of the work is data cleaning, right? So I think there are some tutorials on data cleaning too. So that's another field altogether. But once you have your data cleaned and you have a clear picture of a system you want to design, how nodes are defined and how interactions are working. Once you have that picture and you have cleaned enough data, what are nodes and what are edges, then I guess it goes pretty straightforward way. So like in this case, because someone if someone just gives you a book and says make a network out of it, there are certain a lot of decisions that you had to make to end up with a network, right? So, but those decisions is those are pretty subjective, I guess.
I think I'll add, Paul, you had asked a little bit about best practices. Notice how Riddle has a network actually stored in the form of a pandas data frame. And that's a really, really useful starting point. NetworkX has built-in functions that let you import a pandas data frame as a graph. You will need 2 data frames to store every graph. You will need a node data frame and an edge data frame. It's like having a node list and an edge list. The node data frame stores the list of nodes plus all of their keyword attributes. And the edge stores the edge list. So you have 2 columns, one for the first node ID, one for the second node ID. And then you have all the edge properties there. Notebook 5 shows that, and Riddle in this notebook also shows an example of a real example of how we take a pandas data frame and convert it into a NetworkX graph object.
Okay. So in the 4th cell, we create new graphs, and to populate this graph, we basically iterate through to the pandas data frame. I mean, I'm doing it this way, but there is a direct way of reading it too. But it's nx dot. If you go nx dot from, you have a lot of ways you can read data into this, and so basically, yeah. So you can have a adjacency matrix in itself that you can read. You have you can have a pandas edge list, and this is what is called an edge list, in which you have a you have a source, you have a target, you have and you have attributes about that data. you can run this code like this too, but like to make it more explicit, I'm using a for loop. And this is a bad way of doing it, so don't do it. Use from pandas edge list. But just to make it explicit, like so, I add a source, which is my first node. I add a second node, which is my target, and then I add 2 attributes: the weight and the book. And by doing that, I create these 5 different networks. And let's just look at this network. So in book 1, there is an edge between Jamie Lannister and Loras Tyrell, and there is a weight of 3. So like there are 3 interactions between Jamie and Loras in book 1. So this is our descriptive this is the description of our network, and just like that, if you have edges in all the networks. So now comes the most important part of this tutorial: finding the most important character. Like, how do we do that? Any ideas? We already know what is, like, we already have discussed, what is importance, we know what is degree, what is betweenness. Any ideas how do we find the most important character? Yeah.
First, we have to come to a consensus on what we mean by important.
Isn't that the $1 million question? Yes. We first need to define what importance is, but till we reach a consensus, and we won't. So instead of doing that, like suppose you're given a network data, and someone asks you what's the most important node in this network. So this is how, like, at least for me, this is how I progress. Like I first start with the standard ones: degree, betweenness, or page rank, and there are a ton of other centrality measures. There's load, there is closeness, there's flow centrality. So there are a lot of other measures, but once you know enough about the data, then you can argue that no, this is more important. In this case, we care more about this rather than more about that. So for example, suppose in the airport network, right? I do care about something like number of connections the airport has, like number of places I can fly from this airport. But I also care about making the network connected. For example, I should be able to fly from any city in the US to any other, not directly, but there should be a way. Like the US airport network should not be disconnected. But fun fact, if you look in the 8th notebook, there are some issues with that. The US airport network is apparently not connected. There are airports where you cannot fly to or fly from if you're in New York. But it's not a major issue. But I don't want to give any spoilers, but if you're interested, you can check notebook 8. And yep. So like again, that's how you define importance. And in some cases, you want bottlenecks, and in some cases, suppose you want to, suppose you have a supply chain problem which you have modeled as a network, right? Like you go from warehouse A to warehouse B to warehouse C, and you try to find bottlenecks. In this case, you care about betweenness centrality. You don't care about how many, like how good the warehouse can distribute, but where is the bottleneck? In that you care about that. So let's just start with our standard measures. Let's calculate degree centrality. And if we see in book 1, according to degree centrality, Eddard Stark is the most important character. And people who are familiar with Game of Thrones, this kind of makes sense, right? Yes? Can I get a yes? If you know what I'm talking about. Yeah. Like I'm sorry if you're lost what's happening, what these names are, but trust me, Eddard Stark was an important character in book 1. No, oh, I'm sorry. Oops, sorry. But and as you see in book 5, you cannot see Eddard Stark anywhere. Does that mean anything? I don't know. That's it. So and in book 5, we see that, Jon Snow, Daenerys Targaryen, Stannis, these are important characters according to degree centrality. And these, like, just by looking at these rankings, it kind of makes sense. Like, these are known characters that we, that we predict, these are characters that would be important. So till now, so far so good. Like, the way we modeled our network, maybe it wasn't the best way, but it was in good enough way. So, like, here comes the sad histogram, but it's an important way of looking at this. Is like, because I want to show you the decay thing. In a real world network, it's like, there's a theory of, scale-free networks, and what scale-free means is that in all real world networks, the number of connections, like the degree will always have an exponential decay. That means, like, you'll have some nodes which will have a lot of connections, but majority of the nodes will have less connections, just like Twitter. If you try to plot the degrees centrality of Twitter, a histogram, you'll get something like this. You'll find an exponential decay. That's the theory behind that. And here is that log-log plot, the fancy log-log plot that a lot of academic people love. I don't know why, but because if this was a proper network, not a proper network, but if this was an exact network which was following exponential decay, you would have gotten a straight line. But we get something like a straight line, so we say, oh yeah, maybe this network follows the scale-free property. So in this exercise, we create a new centrality measure because we say that we are not happy with. Oh yes, yeah, go ahead. Yeah, go ahead.
I was just wondering. So, is there a metric to describe the amount of people that? So let's just use Twitter for an example. The amount of people you follow to the ratio of followers. Is there a metric to describe that?
Yes. So, like, in network terms, you say that this is in degree divided by out degree. So, like, for example, when we are calculating degree till now, we are assuming there is no direction to the number of neighbors, right? As soon as you have a directed network, you have something called as an in degree, like, how many nodes are pointing towards me, and then there's out degree. How many nodes am I pointing towards to? And this, like, again, like followee ratio is an important ratio in Twitter analysis. So coming back to the exercise, so I say that I'm not happy with these measures. That I don't like the results. I need a measure that captures more information. So we create this new measure called weighted degree, and instead of just counting the number of neighbors I have, I'm counting the number of I'm counting the summation of the weight on the edges. So suppose instead, like, if I had n neighbors in the first case, my degree is n. But suppose I have n neighbors, but every neighbor has some weight on its edge. Then my new weighted degree is the sum of all those weights on the edges. Does it make sense?
If I'm following you, so what you're saying with the weighted degree, it's how many other important nodes are directly related to me?
Not exactly, no. I'm just saying that I'm not even saying this is a good measure, but I'm not even saying it's a good measure. I'm just saying that I'm just creating a new measure in which I'm counting the number of, I'm just counting the weight that is pointing towards me. Like, I'm just counting that, how close are my connections. Like, suppose as a node, I'm connected to 10 different nodes, but every connection has a weight of 1. And suppose now I'm connected to 4 people, but every connection has a weight 10. So I have very strong connections. Like, I'm not a loosey that I'm not just an extrovert. I'm an extrovert and an introvert. Like, I'm connected to a lot of people, and I have those. My connections are strong. That's the concept of weighted degree. Let me know once you're done. And just as a hint in the exercise, this n here would be a 3 tuple. If you remember from our first notebook, it would have the first would be our the start node, the end node, and the third would be a dictionary, which has attributes. Thumbs up if you're done. And you should get a similar plot like this. As you look on the screen, we have this new histogram of weighted degree and the distribution of that. And again, it doesn't give us a lot of information, but we see a very similar plot that there is some exponential decay in this network. But let's see if it made any changes to our rankings. So we still have ADAT-Stack as the most important node. So not a lot of change. But if we concentrate on this character called Jon Snow, so according to weighted degree, Jon Snow is the third most important, and according to just degree centrality, he is at 5th. So this measure bumped up Jon Snow to 3. So maybe it is a good measure. That was a joke. So you shouldn't choose your measures according to your results. So let's do this for betweenness centrality. And remember, betweenness centrality is the one which always gives you interesting results. Doesn't matter which data set, it will always give you a nice specular result. So let's see if that happens here too. So if we do betweenness centrality for the first book, ADAT-Stack, again, I mean, maybe this ADAT-Stack fella is an important character in first book. Maybe. Like, we have two very different measures. One is degree centrality and one is betweenness. And if you remember that plot, they are not correlated at all because the way they're calculated are very different. And both of them say that this fella name here, ADAT-Stack, is an important person in book 1. So maybe, just maybe, we say that fine, ADAT-Stack is important in book 1. Let's see in book 1. And in this case, we use the term of weights. So if you look at this, you can calculate betweenness centrality because it's the shortest path between a weighted version and an unweighted version. In this, when we take weight, in this we are not taking any weight, we're just looking at the structure. We have ADAT-Stack. And when we look at the weight, which is our number of interactions, we see that it's still he goes to the second position, but he's still important, so not that different. And we'll quickly talk about PageRank. So you don't need to worry about the implementation per se, but the intuition behind PageRank is if an important node points towards me, then I'm important. It's not about the number of neighbors, number of shortest path that's going through me, but it just depends if if an important node points towards me, I'm important. And in turn, if I point towards someone else, because I am important, that node is important. So it's a very neat equation if you want to go into the mathematical details of that. It's a very neat, short and sweet equation, and it works perfectly. So if we calculate a page rank 2, again, Eddard Stark. So maybe, Eddard Stark is the most important character in book 1. But, yep.
Earlier on, you said in the notebook, it says as well that we were doing an undirected network, though. So how does that work with?
Yes. So the thing with PageRank is, PageRank was when it was initially defined, it was defined only for directed networks, but it works both. Like it won't give you the best results for undirected network, and I would still trust PageRank, but it wouldn't give you the best results for undirected networks. But it still works because it's basically it's a edge between an undirected edge is 2 edges, right? It's one in this direction, one in that direction. It still works, but when it was defined for directed networks.
So you said that the PageRank thing had, it looked at the number of links and the quality of the links. So when you're doing an unweighted form of PageRank, is that really similar to degree centrality?
In PageRank, it also looks at the path of the link, like how that link is coming towards me. It's not just looking at the absolute surrounding, but also how it converges. Let me check if no, I don't have the picture here, but we can talk later about this. So and in this we see that if there is any correlation between these, instead of plotting them out, let's see if there is a correlation between these matrix that we just calculated. So we see that there is a very high correlation for some reason between page rank and weighted degree. So if you see, you have a 0.99, this is the Pearson correlation. There's a very high correlation between page rank and weighted degree. I don't have an answer for that, why there is a high correlation. And it does not say anything about these measures. It's just coincidental that you have this very high correlation. Now let's talk about how these measures change, because as the story evolves, things happen, so how the character develops. This is how you can study. You can pretty much port this to any other. You can port this to Harry Potter or Lord of the Rings, and I'm pretty sure people have done that. So you can study, how character develops. How does an important character stays always important, or do they die off, or something like that happens. So let's just plot it for 3 different characters. So these are we have Eddard Stark, Tyrion, and Jon Snow. People who don't know Game of Thrones, these are well-known important characters in the show. So in this plot we see that Eddard Stark, this is the first book. Eddard Stark is very important, and then something happens and he slowly, his graph slowly dies off, and Eddard Stark is no more important for some reason. I don't know what happens, but something happens, and you see that there's a in the third book. After the third book, something happens to Jon Snow, and apparently in the fourth book, Jon Snow is not that important, and here he is, important again in the fifth book. Character evolves, something happens, story changes. So you can try to this is how you can use data science and network science to better understand your TV shows. So let's just work with these set of characters, and in this exercise we basically look at the evolution of weighted degree centrality and how how it evolves for these characters. And so basically this set of characters is is the intersection, is the union of top 5 from every book. So you have like important characters from all the books, and we see how these characters evolve. And you have this nice, pretty looking graph, not so pretty, but nice. And we see that according to weighted degree centrality, we have Jaime Lannister as the most important in book 5, and Daenerys as the second most important. And this was Eddard Stark, and whoops, not so important anymore. So so again, like you can see that the story is evolving book by book, and the notion of the importance of character is changing as you progress through the storyline. And let's see if we get a different. Yep.
Does someone dip below 0 there?
I'm not sure. I mean, I think this goes to 0.
Okay.
Brienne of Tarth goes to 0. Maybe there is no mention of her in book 4. I'm not sure. Let's do the same thing, but for betweenness centrality. And see, because betweenness centrality will always give you nice peculiar results. We have this fella right here, which basically goes, you can see this is a major outlier, and this is not Jon Snow, this is not Daenerys, this is not any Stark. This is, any guesses for people who like Game of Thrones or watch Game of Thrones? This is Stannis Baratheon, and people who don't watch or don't like are like, so what? The answer for so what is, this is not you would something expect. Like, okay, so he's an important enough character, but you won't say, oh, this is the most important character in the network. So this is why the result is surprising, and so this is the betweenness centrality. So what can we say about Stannis Baratheon? Any guesses? Stannis Baratheon is important according to betweenness centrality. What's happening there? Can anyone try to predict what's the storyline here? Why is Stannis Baratheon important? I'm not telling you to actually tell the story, but he has a high betweenness centrality. What does that translate to? Yes, so it basically means that this, Stannis Baratheon is maybe something like this. So if you have read the books or watched the TV shows, at the end of book 4 and at the end of season 6, I guess, you have you have certain events that happen, and those certain events end up bridging multiple communities in these networks, and all those events have one person in common, and that is Stannis Baratheon. And because of that, certain events, we have Stannis Baratheon as node 5 here. Does that make sense? Is that a good enough explanation for Game of Thrones fans? Is it? So yeah, just like that, if we see for a bit degree centrality in book 5, see, even with degree centrality, Stannis Baratheon is important. It's not like he's not an important character. But when you check it for betweenness centrality, if you just look at the ratio of how high the score goes, it's much more in betweenness centrality as compared to degree centrality. This is why always, whenever I get a new data set, I'm like, betweenness centrality. Let's see what happens with that. But surprisingly, I did this for the Indian airport network too. There are no surprises there, so I was disappointed. I wasn't able to find a surprising little airport in India, which is important for the integrity of the structure. It's not. So let's talk about another area of network science, which is called community detection. And this is one of the most hotly debated area, because I think network science as a field is like 20 years old, and still no one has come up with a definition of what is a community. like apparently there are 39 different, not 39, around 30 different ways of what is a community, how you define a community, but no one has come up with there's no consensus what is the definition of community. But in this we use the most famous one, which is called Lua community detection, and which is the same one which is used in the picture that we saw to find those communities, and that picture was drawn using Gephi. So that's if you like visualization, if you are okay with moving out of the Python world, Gephi is an option. And I try to do the same thing, but with Python. So you have this not so pretty looking community. I mean, if I do a circus plot of this, I'll get a much better visualization, But if you just want to have a look of how things are going ahead, you can plot it like this. And we create and these are our communities. Like it's keyed in by 0, and it's keyed in by an integer, and you have list of characters in all those communities. And so I'm not going to explain what is Louvain community detection, but the intuition behind that is the intuition that I really like is you basically try to find clusters of nodes which have high density. And how do you define density? It's like there's an actual definition, is number of nodes, number of edges in a network divided by the total possible number of edges in the network, which is, suppose you have m edges, and which is divided by nc2, because if you have n nodes, you can, and if you pick 2 nodes at random, that's the total number of possible combinations of edges. So it's m divided by nc2. That is the density of a network, and you basically try to find clusters of nodes where this density is very high. So in which basically the intuition is that you try to find clusters in which nodes are interconnected to each other a lot as compared to other nodes in the network. So to see that pictorially, so if I plot a community here, so this is the plot of that community, you see that there are a lot of interconnections. You see this is very, very dense. This structure right here is very dense. So that's a community. And again, if I plot it for any other community, again, you see a very dense structure. Characters in this community all of them are connected to each other. And just to have a look at the actual numbers, if I calculate the total density of the network, it's around 0.04. And if I calculate density of these communities that I found, it's 0.2. So you have these communities are 5 times as dense as the network itself. So this is how you find communities. So we won't do this exercise. So talking about a bit of network science theory, I like to end on this. We talked a lot about Python, a lot about working with real-world networks. So again, you see this beautiful, magnificent plot, right? And okay, so let's go back to 1960s when graph theory was all the rage. All the cool kids in mathematics were doing graph theory, and there was this guy known as Paul Erdos. And does anyone know about Erdos' number? So yeah, one guy knows. Yeah. So apparently, Paul Erdos was a mathematician, and if you have written a paper with Paul Erdos, you get the number 1. If you have written a paper who has written a paper with Paul Erdos, you get the number 2, and so on. You get if you have written a paper with someone who has written a paper who has written a paper with Paul Erdos, you get the number 3. And in the same idea, there is something called as the Kevin Bacon number. Has anyone heard about that? So it's the same idea. If you have worked in a movie with Kevin Bacon, you get the number 1. If you have worked with someone who has worked in the movie, you get number 2, and so on. So, and then there's a Erdos-Bacon number, which is the summation of both of them. So if you have a very low Erdos-Bacon number, that means you are a mathematician plus a movie star. So that's an interesting combination to have. So coming back to Erdos graphs. So suppose I don't give you data. Like right now we have a lot of data, suppose there's an algorithm that you came up with and you want to test this on some data, and you come up with some, you have to come up with synthetic data, right? Then the first question is, how do I generate this? The first answer that pops out, randomly. Yes, you can generate randomly data, but even how, like, which, okay, so you generate normally distributed data, but how does that translate to networks, right? So that was the first question. So I think Paul Erdos came up with this model. It's called Erdos-Renyi model, in which suppose I give you a probability of 0.5. So you basically go to every 2 nodes, like you pick 2 nodes, and with a probability of 0.5, you add an edge. So this is how you end up with a random graph. This was in 1960s, and in late 90s, another model was proposed, which was called Barabasi-Albert graph. And in this model, the idea is that most of the, like this is what a real world network looks like. Most of the nodes are connected to, like a small number of nodes, but there would be one node who's connected to a lot of nodes. So like if you look at the histogram plot, I'm sorry, Eric, but histogram plot. This is the difference. If you look at, okay, like because histograms are not nice, you don't see a nice plot. But if we increase the number of nodes, we'll get a much smoother plot. So yeah, this is the plot of Erdos-Renyi graph and the degree distribution of that graph. It's a normal distribution. It's not a normal distribution. It's not a normal distribution, but it peaks at 0.1, as you see, because I put in the probability as 0.1 of having an edge. So it peaks at 0.1. So you have this nice looking random graph. And then you have something like this. This is the Barabasi-Albert graph. And if you remember, this was our degree distribution for our Game of Thrones networks, right? So which is much closer to a real world as compared to something like this. Because these two are very, very different networks, right? Like structurally very different. How this is, how the degrees are distributed here and the degrees are distributed here. If you plot the ECDF of this, you'll get a smooth S curve. And if you plot a ECDF of this, you'll get a cliff, which is what most real world networks will give you. So, and this is our log-log plot. If you were interested in this, this is the log-log plot of a Erdos-Renyi graph, and this is the log-log plot, which is our straight line of a Barabasi-Albert graph. So this was my detour to a bit of network science theory. And if you want to talk more about this, I'm here for the next 8 days. So, and there is still a lot of material left in the repository. There is book 5, 6, 8, 3 bonus notebooks. So if you are more interested, there is a lot of more material. Feel free to go through it. Feel free to talk to Eric or me during PyCon. So thank you.
We got a few minutes. We got a few minutes. Myrtle's got some announcements, and then if there are questions that people want to ask right now and leave for posterity on YouTube, we're happy to entertain them as well.
So lunch is at 12:20, so that's in 2 minutes in Grand Ballroom A and B.
So any questions from people that are burning questions? All right, so Paul, you've asked a lot. I'm going to go to the back first. Sorry, I misunderstood. All right, so Paul, you get the first one.
What are the most interesting areas where you could apply this in prediction in data science? So the open triangles is obviously one, but what are the other ones that are out there that we might want to take back to our respective institutions?
I mean, I guess that's a very particular question. It depends where you work. I could probably, so we can talk later about that, right?
It's quite highly context specific.
Yeah.
What are some interesting networks you've seen that maybe didn't seem like it makes sense as a network at first until you start looking at some of these plots?
I mean, I'm not the best person to ask this question because I've been doing networks for the last 4 years, and whenever I look at some data, I'm like, oh, that's a network. So it's like, but last week I started working on some spatial networks. It's like how you, I mean, it's a very, like if you try hard enough, you can make spatial points as networks. So, like last week I was working on that, but for me, I have a bad habit of like, oh, that could be modeled as a network.
I think that speaks to like, once you get used to this network way of thinking, it becomes very natural to take a row, like to take your data table, which in which each row is basically a node, and start asking the question, how are the rows related to one another? And then once we find a good definition for a relation, suddenly we have a graph. And now we can ask questions about the relationships between the nodes. That's a quote that I have in Notebook 2. The heart of a graph is not in its nodes, it's in its edges. The edges are what make a graph interesting. The relationships between the nodes are what make a graph interesting. Now, there have been questions before about scalability. Before we go to the last question at the back. Is that on scalability? No, okay, but before we go to that question on the back, I just want to put this out there for everybody. NVIDIA is working on cuGraph. And I've been on GitHub talking with the NVIDIA developers to make sure that cuGraph's API accelerates graph algorithms and matches NetworkX. So hopefully within the near future, on some undefined time frame, we'll be able to have NetworkX APIs on the GPU.
They recently had a very big project, this thing, right, with a lot of researchers and
yes.
like,
yeah. So final question at the back.
So obviously the math is fantastic, but do you find that you actually use the plots to kind of investigate? I mean, they're great to look at the visual graphs, but are they useful for investigating kind of, I don't know, your ideas about how the network is working or how it behaves? Do you find that it's more than just I don't know, you start seeing patterns that kind of repeat, that you're like, oh, I see where there's a problem in this graph or network?
Yeah, like for example, if I know, like if I look at a plot like this, I know that the graph has the scale-free property, and once I know that, I know that the scale-free property defines that there are less nodes with a lot of neighbors. So like I can start thinking towards that direction. And for example, with an ACDF plot, I know exactly how what's the percentile distribution, right? And like I'll just know a lot more about the data, and then I can start thinking from that way forward.
So it does come with experience. The more you do it, the more familiar you are. That said, visualization is like one of the biggest tools that we need in any type of data analysis, right? So that's why we have them. And these graph-specific ones, hopefully, are useful, right? So for example, we had that, the exhibition one, like we would not have, if we didn't choose the right visualization, we would not have been able to immediately intuit that inference that, oh, yeah, people are just local in time, connecting with one another, right? So visual inferences and your visual toolkit, very important. Cool. Well, thanks for coming. Thanks, Mriddle. Let's give a hand for Mriddle. The apprentice is really the master now.